Good morning, everyone. Welcome to our final webinar, Implementing Leading-Edge Technology for Design Revolution. My name is Shari, and I'm the Marketing Manager at ASIC. I'll be serving as your moderator today. Okay. First of all, I would like to thank you all for visiting our virtual booth during the Samsung SAP Forum last week. As the technology partner of Samsung Advanced Foundry ecosystem, we would love to share best practices on libraries and memory compiler plan for Samsung process, high-speed files IP solution, and ASIC design service in advanced nodes. If you have any question, if you have any question for the presenter, you may send in your question at any time during the presentation. We will collect these questions and address them during the Q&A session at the end of today's presentation. Now, let's please welcome our first presenter, Shahbaz Abbasi. Mr. Abbasi is the staff design engineer of the IP team of ASIC. He is the expert on analog and mixed signal IC design. He will be speaking to us on library and memory compiler for Samsung 14 and 28 nanometer. Welcome, Mr. Abbasi.
Thank you very much, Cherry. Hello and welcome to everyone who is joining us today in this webinar. I'm going to be covering the topic of libraries and memory compiler for Samsung 14 and 28 nanometer process nodes. Right, so I will be going through the plans and offerings of ASIC. So to start with, if I was to begin with libraries, right, so ASIC offers mainly a set of 3 libraries, right, namely normal library, low power library, and high performance library. Right, the low power library allows for applications which require longer battery lives, right? Such as biomedical devices, for example, implantable devices, which require high energy efficiency, for example. And then another set of library is the high performance library, which offers a much higher speed for applications which don't compromise in speed. For example, gadgets, tablets, smartphones, right? So this library fits well for those applications. And the normal library is essentially a trade-off between the power efficiency and the performance, right? So combined, these libraries offer a unique set of options for the SoC designer, to optimize their products for speed, for example, for area, and for various various performance characteristics. Right, so ASIC intends to offer these libraries for Samsung 14 nanometer and 28 nanometer technologies, right? And ASIC also intends to port its libraries to such technologies by enabling, by also shortening the lead time. Right, so I will be presenting how ASIC plans to do this for libraries and for the memory compilers. Right, so coming on to the memory compiler now. So the plan that ASIC has for memory compiler, and the team is currently busy developing this compiler platform. So it's basically going to be a highly automated and intelligent compiler for various types of memories, such as SRAM, register file, and ROM, right, which are highly needed and in demand for various SoC applications these days, right? So ASIC plans to improve the PPA at both cell level and at the floor plan level, right? By performing the relevant optimizations, because we have found that the main performance bottleneck when we go from a technology to another, it's more or less from the cell level rather than the floor plan level, right? So based on the desired performance inputs, which will be coming from the user, such optimizations will be made on the fly, right? And ASIC plans to have a flexible architecture to enable fast porting between technologies, right? So because one of the most important things is the lead time, right? When we want to offer our compiler or even our standard cell libraries for a certain technology, it's best to shorten the lead time. And so we need good porting strategies, intelligent porting strategies, a nice framework in which the technology porting feature is embedded, right? And so it can be utilized to reduce the lead time. So this is actually involved in the QSIC plan. Right, so why do we need a memory compiler? In an SoC, memories can be an important power and performance bottleneck. Right, so you can imagine that fully manual design and verification for such a block can be resource consuming. And so optimal memory and logic design in a timely manner is very important. And the good thing is about memories is that they offer a regular structure, which lends itself pretty well to automation. So this can be exploited, right, as far as memories are concerned. And so the advantage of doing this would be that a memory compiler would actually offload considerable workload from the design and layout teams by automating most of the part of the memory compiler, right? So as you can see here on the left side, it's the typical framework for memory compiler. We have a configuration input, some custom cells drawn by hand, and a set of rules which come with the technology. Right, with these inputs, the memory compiler basically produces these files such as the GDS, netlist, and other collateral files such as the behavioral model, datasheet, and so on. Right, so moving on, yeah. Like I mentioned already, the lead time problem. Let's say if we want to port our compiler from technology A to technology B, right? So depending on the technology nodes, this can require a lot of redesign of the custom cells in particular. And it can take up to months or even years, right? And it can have a huge impact on the lead time. And so, especially when we are talking about technologies such as FinFET, so compared to the bulk other conventional CMOS technologies, they are pretty different, and the porting can take a lot of time, right? So the motivation behind building this compiler for key ASIC is to reduce the lead time as much as possible by building such a framework for the memory compiler. This framework should be able to take in the relevant inputs in a very flexible way, and it should be able to accept templates very easily and flexibly in order to allow porting from one technology to another. Right, I will be explaining this in a bit more detail in the subsequent slides. So the vision that Key ASIC has, like I mentioned, is to develop a compiler platform that offers flexible technology configuration, first of all, right? Supports advanced technology nodes, including FinFETs, right? And generates optimized cell and memory GDS based on the provided configuration, which of course comes from the user, and also a set of performance criteria, again, which comes from the user, right? So the strategy that QASIC has is to do optimizations at both floor plan and cell level, right? By selection of the cells appropriately based on the required performance by the user, right? And the next thing is to automatically generate these cell layouts. And there should not be a need to design the cell and do the layout of the cell every time porting is required, right? There should be templates. There should be flexible ways to easily modify the designs and optimize and the layout, and automate it as much as possible. So in addition to this, of course, the collateral files like the netlist, the behavioral model, and the datasheet, validation reports, all of these also need to be generated automatically. And when the compiler needs to be ported from one technology to another, this should not increase the lead time, right? So this is the overall vision as far as the memory compiler is concerned from ASIC. Now, if I talk a bit about the porting challenge that we have found and that our team is working with, is it's mainly the bottleneck, I would say, is the block level design rather than the floor plan. You see here, as I've shown here, the floor plan takes only a small chunk of this challenge space for the memory, right? So our aim for this memory compiler and our plan to build this framework is to build block level compilers that would generate the block level cells, designs, and layouts and optimize them automatically, and with the minimum amount of effort required. And like I already mentioned, it should be able to accept templates for these cells. Moving on, the overall strategy is to make the code flexible enough so that it's robust to handle proportional changes in the layout cells. Right, it's very important. And then auto-generate the block level layouts, right, through these designs which we called block compilers, through these programs actually, which we call block compilers, right, for all the subcells that would be the building blocks of our memory, right? And in addition to this, the memory compiler should be able to enable easy configuration of placement patterns. So for example, if we want to change the floor plan, right, so it should be configurable and easily done by only changing a few parameters in a few configuration files, for example, and should not require an entire change of layout by drawing a layout. You see how this can reduce the lead time, right? So as I mentioned, block compilers, a typical block compiler would look something like this. Its inputs would be the performance criteria, which will come from the user, right? The technology files for the specific process node, and of course the bit cell GDS, because and the bit cell comes with the technology and it has a fixed size constraint, and so this has to be used to decide the overall size constraints on the various building blocks of the memory, right? So the bit cell GDS is very important and a very important input for the block compiler, right? And based on these inputs, and the block compiler essentially optimizes the design automatically, and it generates a layout based on the DRC rules, right? And it also generates the netlist for that block, right? So this is the entire idea behind the block compiler. So one example of a memory compiler flow is here, right? Based on the user input, we select a floor plan, right? Like I already mentioned, we intend to keep our floor plan configurable, right? And so we have a pool of floor plans, and we are able to select the floor plan from that pool. And then we set the block sizes based on the bit cell, right? And then we invoke the block compilers with all the relevant inputs, and we generate the GDSs and the netlist for all the subcells in the memory, right? And then these subcells are fed as input to the compiler core engine, right? Which basically stitches them together according to the desired performance criteria and the user input, and it generates the final GDS and other collateral files, right? So the unique thing in ASIC's memory compiler platform is the block compilers, right, and the floor plan selection, right? So in this slide, you can see the various components of the memory compiler, including the compiler core, which is the main engine. All the inputs essentially come to this engine core, right? And then we have the block compilers, we have the collateral files generator, the placement patterns. These are essentially the configuration files, right? So with all these inputs, the compiler core is able to generate a GDS and other collateral files with the use of the collateral file generator, right? And so these are the overall components which complete our compiler. And like I said, the main vision of ASIC of having this platform, of this framework for the compiler, is to reduce the lead time by enabling faster porting for between technologies, right? So that's the main motivation behind this, and this is what KeyASIC is planning to offer, right? So to summarize the libraries and memory compiler topic, so KeyASIC aims to develop flexible standard cell libraries and memory compiler platform to automatically generate PPA optimized designs and also to enable faster porting between process nodes, right? So this is the main vision. And so these are also targeted at advanced Samsung process nodes, such as Samsung 28 and 14 nanometer technologies, right? So because 14 nanometer, for example, is a FinFET technology, so it requires, probably different design, and of course, the layout problems are different. So we also intend to include specifically this part in our compiler uh, separately for the FinFET technologies, right? Separate templates, for example, separate design optimizations, separate layout optimizations, and so on. So we intend to include this in our memory compiler platform. So finally, KeyASIC is right now in the process of patenting its various technologies and techniques that have been used or are being used in developing the memory compiler and standard cell libraries. So that would be from my side. Over to you, Cherry. Thank you very much.
Thank you. Thank you very much, Mr. Abbasi, for addressing this knowledgeable session. If you have any question for Mr. Abbasi, please add them into the chat function, and we will be able to answer some of them during the Q&A session. Okay. Now let's move along to the next session. Let's please welcome the next presenter, Muhammad Iskandar Binzari. He's the engineering and the staff design engineer of the IP team for KeyASIC. His specialties is I/O design, and he will be sharing the high-speed PHY IP solution for us. Welcome, Mr. Binzari.
Thank you, Sherry. Today I would like to discuss on the high-speed PHY IP solution from the KeyASIC. So this is one of the IP that we are working currently right now. Okay. So the agenda for today's discussion is more to the first agenda is the KeyASIC PCIe PHY description. So we're going to discuss on the features of our current PCIe PHY. Second agenda is KeyASIC PCIe 5.0 block diagram. So we are going to go through each block each block diagram in our PCIe 5.0 architecture. So the third agenda is to discuss on the TX driver specification and also the issue and solution that we are currently in progress now. So the fourth one is to discuss on the KeyASIC patent filing. We have filed 2 patents for this project so far, and we are planning to file more patent from this project. And the last one is to the summary of this discussion. So let's go through the first agenda, which is PCIe 5.0 PHY description. So the KeyASIC KeyASIC PCIe 5.0 actually support the backward compatible of the PCIe. Means that we also need to support PCIe 1, which is 2.5 gigabit per second, PCIe 2 5.0 gigabit per second, PCIe 3 8 gigabit per second, PCIe 4 16.0 gigabit per second, and also of course PCIe 5 32 gigabit per second serial data transmission. So KeyASIC PCIe 5 also support low power transmitter features. So this one we discuss in the next slide. So KeyASIC PCIe 5 also have a tunable ultra bandwidth with a T-coil. So we use T-coil to enhance our bandwidth of TX and also RX. So at the same time, the PCIe 5 also have a 16-bit or 32-bit pipe interface between PCS and also PMA. So we also have a CDR, clock data recovery, and also serializer and deserializer block. And also we have a beacon transmit and detect features. We also support power saving modes, encoder, decoder for 8-bit to 10-bit, and also 1 to 8-bit to 130-bit. So 8-bit to 10-bit is used for PCIe 1 and 2, and 1 to 8-bit to 130-bit encoder is using for PCIe 3, 4, and 5. So we also have a receiver detection, tunable RX CTLE peak range, and also tapping DFE. Loop back test and also built-in self-test for testing purpose. And we also support ESD IO protection, HPM 2 kilovolt, MM 100 volt, and CDM 500 volt. So this is a description of features of our KSIC PCIe 5.05 description. So the second agenda is to discuss on the block diagram of our KSIC PCIe 5.0. Okay, as you can see here, the block that we are developing now is the physical layer. So it consists of PCS and also PMA. So PCS means a digital block, and PMA is more to analog block. So signal from the controller, there are 32-bit signal from controller. We go to our file layer. We go through the PCS, go through TX logic, then it will be encoded. The signal will be encoded in the PCS level. Then it will send through the PMA block. So inside the PMA, TX blocks consist of a parallel to serial converter, and the serial signal will go through the feed forward equalization block, and the signal we go through the driver. This driver we implement the low power driver here, which we implement the hybrid method for the low power. So then we also have then this TX and RX will be controlled by the same bias in the common block, and also the PLL, which convert 100 megahertz signal, external signal, to 500 megahertz signal. So we also have a RX block here. So when we receive the signal from outside, it will be equalized and convert. The signal will be converted from serial to parallel and transmit back to the PCS block as a logic signal. So we have an elastic buffer. We also have a decoder and RX logic. So 32 bits will be sent back to the PCIe 5 controller. So this is the TX driver specification and solution that we are going to discuss. So as we can see here, for PCIe 5, we have a few preset. I think around 11 preset we need to meet. So the P4, P1, and P0 here is for PCIe 1 and 2. So PCIe 3, 4, and 5 will be at another 8 preset. So difficulties that we face when we design the TX is to fulfill all these preset requirement. So we need to set the coefficient accordingly with the specific specification. So after we set the coefficient, then we should meet all these 11 preset conditions. So this is an example of the TX driver at preset 7. If you look at preset 7 here, so we have VA, VB, VC, and also VD. So VB and VA is a de-emphasis, and VC is a boost, and VC is the pre-shoot, and VD is a boost. So we need to fulfill this requirement for PCIe 5. Okay, so when we design this TX block, actually we based on two specification, which is a base specification and also CEM specification from PCIe SIG. So we are using version 5 for PCIe 5.0. So when we start to design this TX, we implement we model all the preset before we start the circuit design. So this is an example of modeling simulation that we have done before we start any circuit design. Okay, so for TX driver, like I mentioned before, our objective is to lower down the power. So we're going to operate in the low power design. So we have choose the hybrid architecture. So this architecture also we going to reuse in our next file development for USB, HNC, and also SATA 3.0. So the hybrid architectures here means is combination of VM and voltage mode and also current mode driver. So as you can see here, this is example of the current mode driver. So we merge with the voltage mode driver, and we have it produce the hybrid mode driver, something like this one. So the current mode will control the coefficient that we have discussed in previous slide. So while the VB voltage VB that we discussed in previous slide will be controlled by the voltage mode driver. So we also have filed so far two patents for this project. So the first one is the TX coefficient control with the 6-bit DAC. This one is inside our driver. We have a current mode driver. So we use 6-bit DAC to control all the coefficient that we have discussed in previous slide. So so the second pattern is a voltage mode TX impedance calibration with 3-bit ADC. So instead of using a few legs of digital driver to control the TX impedance, we use some kind of analog method to control the driver impedance. So we use ADC to control the analog side of the driver to calibrate the driver impedance to remain always 50 ohm at PVT condition. So we plan for another pattern for this project, but so far only these two is official one. Okay, so summary for this discussion is ASIC is actually is a strategic partnership with Samsung to deliver the high quality of PCIe 5.0 IP. So ASIC will deliver the best in class PCIe 5.0 with Samsung 14 nanometer process development. So as everyone knows, this project is still in progress now. So the tape out for this project is planned to be end of May 2022. Okay, that's all for my presentation for today. Thank you. Back to Cherry.
Hello. Okay. Thank you, Mr. Bizarri, for that excellent presentation. Again, if you have any technical question, please reach out directly to us via the chat function. Okay. Now let's welcome the last presenter for the final session, Mr. Xinkai Li. Mr. Lee is the Vice President of Marketing for Key ASIC. He has a vast knowledge of the product marketing of the ASIC. He will be speaking to us a very timely subject, ASIC implementation for Samsung advanced nodes. Let's please welcome Mr. Lee.
Thanks, Jelly. Ladies and gentlemen, thanks for your time to participate in this webinar for ASIC. Next session, I will introduce the ASIC implementation methodology for Samsung advanced nodes technology. Here we have a brief introduction of the ASIC. The company was founded in 2005, and it was publicly listed on Bursa Malaysia market in 2008. And we have offices in Malaysia, China, Taiwan, and Singapore. Technology-wise, we have more than 150 analog IPs to serve different locations in the market. And we have a standard cell libraries to cover the requirement of high performance, low power, and small area. And we have been working with worldwide advancing foundries to serve our customers with the most valuable technology. In terms of the technology, we have a solution for 180 nanometer, 180 micrometer, and 40 nanometer. We also have a different technology such as CMOS, silicon germanium, SOI, or silicon carbide. And business core. Actually, we have a ASIC design service can serve the customer from spec in to chip out requirement. And we have our own products to serve customers with IoT and AI SoC chips. These chips will also include in hardware, software, and app design. The system design-wise, we can do a full product design and manufacture for our customers. And this slide, we can see a lot of customers in the worldwide area. So we have customers in North America, Europe, Asia, and the rest of the world. This is a system level customers that we've been selling our own chips to those customers for their end product. So we have a lot of worldwide brand customers to implement their product with our own chip and our own platform. Operation, here we have some office in China, Shanghai, in Hsinchu, Taiwan, Kuala Lumpur, in Malaysia, and in Singapore. Here is our revenue trend. So in this year, 2021, we forecast to reach about $50 million in this year. Next session, we will introduce the ASIC design service flow. All right. Actually, this is a key ASIC's role in the business area. So in here, we have a low-level supplier is a Foundry, and we have a very high-level product suppliers who can provide system product. And also, we have customers to do SSSP chips by themselves. So in between those two end of customers, where our value is to first, we can provide the IP design service and design kit to the Foundry. So Foundry can easily provide those platform to their customers to do their chip design. And in another side, another end, we can talk to the system companies or SSP companies to do the turnkey design service for them, so they can leverage our own resources to build their products quickly and effectively and correctly. So this is the role that KSK can play with our end customers. Okay, now talk about the technology division. Then here we have 3 levels of engineering divisions. The first level engineering divisions is the product of CSSP and system products company. For those customers, they are looking for chip, system, OS, driver, and applications to implement the to product development. And for those customers, we can provide a wafer, chips, and system board and software to serve their requirement. So the customer level will be covering all system ASIC companies in this area. The second level of engineering division we are talking about is the ASIC SoC implementation and optimization with design methodology, the tool development, and platform. So for those level of customers, we can provide the wafer, chips, NRE, and the platform building for the customer's requirement. The customer target will be system ASIC fabless design companies who can build their chips and their systems with our own service scope. The third level engineering division will cover the design and the foundry enabling, such as PDK, standard cell, the memory compiler, I/O, the analog IP, and the CPU, USB, etc. Low-level IPs in this level. In this level, we can provide the IP and the PDK design flow and the calibration data to serve our end customer. The end customer will cover the foundries, fabless design companies in this area. We have a very comprehensive experience to work with worldwide customers, either system companies or chipset companies, to provide our platform service to them. Here are some examples we have been engaged in past years with our worldwide customers. In European area, we have tape out in 2014 on DSP chip is running 200 megahertz with Stera 130 nanometer process. And in 2015, we tape out two chips. One is a navigation SoC, including an ARM Cortex-M3 core on Stera 130 nanometer process. The second chip was a navigation RF chip. It was designed on TSMC 180 nanometer silicon germanium technology. And from 2016 to 2020, we actually also tape out several chips based on such as backend SoC with ARM 1176 core. This is on Fujitsu 65 nanometer technology. And we also tape out a ultra speed DSP chip with ARM bus. It is on Foundry 65 nanometer technology. And we also tape out a USB 5 for European customers on 130 nanometer technology. In Japan, we have tape out a very hard chip with Japan customers. The chip was designed for the Game Boy controller on the cartridge. It was done by Stera 130 nanometer technology. We also deliver a USB 2 device file on Panasonic 65 nanometer technology, so they can enabling their IP business with our strong supporting. In North America, we have a chip tape out in 2008, which is a video SoC chip on IBM 65 nanometer technology. In Asian areas, we also sign off a APR design of APGA chip on TSMC 2028 nanometer technology. And this chip is actually finished in 2011. And in here, Taiwan, of course, we have many chip designs in the past several years. In 2012, we have commercially shipped the first Wi-Fi storage SSP SoC, which is a core based on ARM 926 core. It's on Stera 130 nanometer process, which has a very strong sales, contributed more than 1 million pieces shipment in 2013. And in 2018, we tape out two 130 nanometer ASIC chips. It's for video processing application. And in 2019 to 2020, we tape out two 160 nanometer ASIC chips. It's for small panel controller. And this chip is quite hard sell because it can support the CPAP, the breast checking machines, medical machines, to predict, to treat, the COVID-19 disease. So this machine has been selling more than millions in the year when he launched to the market. In 2012 to 21, we tape out a 130 nanometer ASIC chip. It's for surveillance application, which is very strong demand. It's a very, very strong demand in Asia market. And here, talk about the service offering model. For ASIC design, our company can provide different level of service to customer. If customer, they are looking for a company to the full turnkey, which means ranging from architecture design down to timing analysis and in the GDS tape out, we can do the full design process for the customer. Or if a customer, they can do the architecture design by themselves, and we can take over the design from RTL, and then we move down to the GDS tape out. Or customer, they can do architecture design and RTL by themselves. KSK will handle the get timing design, which is physical design process, and layout verification down to the GDS tape out, and then that for customers. The last case is customer can do most of the things by themselves. So KSK will only do the layout and the verification, and then tape out to Foundry is for customer. This is also a workable model for us. The slide will show the IP focus on our company. So we have a lot of IPs to support the different application for customer. The first category we can support the customer is the audio video area. So we have a lot of ADC, DAC, voice codec, and audio codec, which can be used for different applications such as multimedia, phone application, portable electronic devices, Wi-Fi, WiMAX application. So we can provide the different codec for those four applications. And the power management, we have a lot of voltage regulator, power reset, DC-DC converter, and bandgap reference chip IPs to support the application of the same four areas. And protocol and I/O area, we can provide a USB 2.05 and SD1 DSDR50 IP, DDR25, SST05, SATA IDA control and 5, and the SATA 5, PCIe 5, Ethernet 10, 100 mega 5, and the CPU I/O, and the universal car bus. So we can provide those high-speed 5 SerDes IPs to save our customers' effort to design the chip. The clock and the components, we can provide PLL and RTC and the DLL to implement the power management functionality on customers' low power application chip. For high-speed service and the low power components, we have a very strong library called Keywheel, and we can provide all these high speed and the low power components in different process. And we have a high speed RAM, high density standard cell library, and the VROM and the high speed RF IPs for all the application area. The CPU wise, we have a very strong hardening IP on ARM Cortex ARM 926 and ARM 946 CPU code. Those are all target on the high-speed and low-power SoC application. Okay, KSK not only provide the chip design and the chip implementation only, we actually can provide a one-stop solution for production and testing management. For product engineering MPI space, we can develop DFM, DFT test plan spec for customer. We can manage product qualification project, and we can perform product calculation, transfer design to wafer fabrication foundry, and manage product definition or for system and BOM requirement. So we can address customer issues on the NPI level, and we can manage product yield and the control testing and the quality test and the cost control. For test engineering and QA, we can manage test hardware and software project, and we can transfer product to test site. We can dispose suspected material in testing, and we can implement a long-term QA program, manage document control, and address customer issues for testing and qualification assurance. In testing development activity, we can do a testing hardware software development and manage the reliability in board level verification. We can also manage the reliability test activity for customer. Look down to the production planning and the control. We can manage manufacturing plan system and implement the capacity planning process. We can also do forecast and the building plan, packing out, and the shipping service for customer. So we can manage all the backlogs for customers based on their computer system. So we can track and control inventory very effectively based on our communication together with customer. And down to the packaging engineering, we can manage design rules, design and developing packaging, including package outline design, substrate design, bonding diagram, and a BOM for the overall package design development. We can also define package and the marking packing specification, improve the package yield, cost, and reliability, and also dispose suspected materials in assembly level. We can do all those things for our customer. Finally, the overall production activity, including a wafer fabrication, assembly operation, testing, visual, packing, shipping operations, can all be done by ASIC to leverage our internal very strong experienced teams. So customer can leverage this ASIC ability to save their manpower and their loading to make these all things happen in time, on time, and under the required cost. So that's all my presentation. I will send in the time back to Sherry. Sherry?
Okay, Mr. Lee, thank you for your amazing session. And now we're now going to begin answering the questions submitted before the event and during today's presentation. As a reminder, you can still submit questions in the chat feature. Okay, I have a question to Mr. Abbasi. This question is, how will you automate the block compiler such that it works for every new technology that you port the memory compiler to?
Okay, so like I had mentioned in my presentation, we intend to build a framework for the compiler in such a way that it accepts templates for the various block compilers, right? So whichever subcells are there in the memory, uh, the compiler framework will accept these templates, which will be which we can change for different technologies. So whenever we want to optimize a design for a certain technology, right, or change it or change the layout, right? So for a set of subcells or for many subcells, then these templates will have to be modified accordingly, and then this is what will help with the automation. Yeah, I hope that answers the question.
Thank you for your answer. Okay, now we got two questions to Mr. Benzari. The first one is, what does the target application for key-ASIC PCIe 5.0?
Okay, so at the meantime, we are targeting AI and also HPC application. So in future, we are targeting for automotive, for sure.
All right.
Yeah.
Okay, sounds good. Okay. Next, another question is, what makes key-ASIC PCIe 5.0 is better than others?
Okay, so when we do design for our PCIe 5.0, we always take care on the PPA, which is a power, performance, and also area. So for example, in term of power, we are implementing hybrid architecture for our TX driver. And for example, for area, we implementing TX analog based impedance calibration, which is very small compared to digital based impedance calibration. So these two examples shows that we are moving forward to have a best in class, or I can say best PPA. So that's why KSIC PCI 5.0 is better than our competitors.
Okay, great. Thank you for your answer. Okay, any other questions? All right, it seems no questions so far. Well, sorry. Okay, thank you to all our presenters today, and thank you for attending this webinar. If you have any additional questions for our presenters, you can ask them in the live chat feature on our website. The website is www.keasic.com. We look forward to chatting with you online. Again, on behalf of KASIC and our presenters, thank you for joining us today, and have a blessed Thanksgiving. Thank you.
Thank you.